they had like the clouds and everything behind it. Is this the water Bible?
I like it. Okay, so talk about here now, the next feature, we're almost done, pretty good. We're talking about viscosity, also known as suspension. They work together. Okay. Viscosity is thickness. And the thicker things are, the easier it is to hold things up. So solid matter, so this is not dissolving. There's a big difference between these two. Solid matter can be suspended in water. So, non-polar organic matter can be suspended in water, like sediments and pieces of garbage, little tiny algae, all that stuff that Greenwood studies can be suspended in water. And also what can be suspended in water are non-polar gases. A non-polar gas does not dissolve in water, because water is polar, but it can be suspended. Okay. Velocity, how fast the water is moving, affects viscosity. And we all know that if I could take my hand and put it very slowly into water, or better yet, I could jump into water, and if I'm 2 feet away from that water when I jump in, water's really soft. But if I'm 30 feet away from the water and I hit it, the velocity and increase the viscosity of that water to the point where it's going to hurt. So again, you don't want to go that far. So speed. And so as viscosity goes up, its ability to carry particles goes up too. I can suspend more particles. Okay. This is how a pressure washer works. Put water at high speed and it'll pick up particles. So I can tear things up. Okay, I already talked about using water as a cutter. Basically that's how you're doing that. So when water is traveling very, very fast, we call it erosive, because it picks up particles. If I slow it down, it loses viscosity and it becomes deposition. Starts dropping. And so when we talk about rivers and streams, flow is not constant. And one of the places where you really see this a lot, okay, stream systems. I left my pen in the room. Yeah. Okay. So if I look at a stream channel, I hate to do this to you all. You can look on this way here.
I don't think that's an expo marker.
Say what?
I don't think that's an expo marker. It looks like a Crayola marker.
Okay, anyway. You're probably right. I should better not use it. So, when water is in a stream channel, okay, so it's in this channel. Oh, thank you, sir.
I don't know if it'll work.
Works better than what I was going to do.
I think they'd be pissed at you.
Yeah. So let's say I got this. We got what's called the floodplain. We have the stream channel itself and the floodplain here. Okay. So the water in this channel is moving at a pretty high velocity. Okay. Do that channel here. If this river then goes into flood mode, so it's carrying a lot of material. If it goes into flood mode, so if the river is this high, it's moving pretty fast. But if the river goes into flood mode and the top of the river is up here, because it's spread out now, it loses its speed. And so as a result, right here, what happens is you get, on each side of the river, you get these lumps, because that's where everything starts to fall here. Okay, when it first comes out, the velocity goes down and everything drops here. These are what are known as natural eddies. And what's causing it is change in velocity, the stream system. If you ever look at, have you ever seen a pond? Where is the shallowest part of a man-made pond? Where's the shallowest part?
On the edge?
Yeah, on the edge. Where's the shallowest area? Usually it's the upstream area, where the stream comes in. As the stream comes in, opens up into the pond, loses velocity, and so ponds tend to fill in from their upper end where the water's coming in, because that water's being slowed down. We'll talk about lakes later. Lakes have a life. They're born, they live, and then they die. And how they die is through sedimentation. Temperature affects viscosity. This is kind of important. That, okay. But it's the exact opposite of affection of solvency. The colder you get water, the more dense it becomes, to a point, in general. So as I warm up water, the viscosity goes down. As I cool down water, viscosity goes up. Have you ever heard of one of the common measurements of water condition is called dissolved oxygen? What is dissolved oxygen? Bullshit. There's no such thing as dissolved oxygen. Oxygen does not dissolve in water. Okay. Let's get in here. Dissolved oxygen, okay, remember, it really isn't dissolved. It is suspended oxygen.
Because it's not polar.
It's not polar, right, but it's suspended. So as you warm up water, the dissolved, quote unquote, use the term, we're going to be using the term DO, and I don't care if you use the term DO, as long as you realize it's not dissolved. Okay. The dissolved, as you warm up water, it holds less and less oxygen. So that is a big difference here. So a lot of people have trouble getting their head around that. Okay. So that's kind of important. That's kind of like dissolved oxygen. No, that's it. The other thing is what is known as dissociation equilibrium. Okay. If you've had any sort of chemistry, it should all be second nature to you. All these sort of things here. Dissociation equilibrium. What does that mean? Okay. Water, H2O, ain't always H2O. It's gotta be different. So not always. Most water, you know, if I have, if I had about 6 million water molecules, most of them would probably be H2O. Okay. But there's one clown every so often does this, splits, and forms, so H2O forms the cation hydronium, hydrogen ion, and the anion hydroxyl. Okay. This happens, so it means that when you have a big, huge container of water, not everybody is H2O. Somebody's doing this. Okay. So under normal conditions, it doesn't happen a lot. Under normal conditions, for every molecule, I should say split, you can't see it here, every molecule that splits into hydronium and hydroxyl, there are basically 10 million that haven't done it. Okay, so it's 1 times 10 to the 7th. So it's not real common, but there's a whole lot of, you know, think about it. You know, there's a lot of water in the world. So there's everybody else, so only one of them does it for every 10 times 10 to the 7th water. This is an important number, 10 to the 7th. What that means, normal pH is 7. That's where that comes from. What it's telling you, pH, of course, is just all, pH is the concentration of hydronium ions. They couldn't be measured by hydroxyls, but really not. How many, pH is a measurement of how many H pluses are floating around in the water. So you have a pH of 7, that means that there's one of them for every 10 million. If there were 10 for every 10 million, it'd be 1 for every 10 to the 6th. So pH would go to 6. pH would go to 5. So we're talking a lot about pH later on. Okay. Wrap up the last thing here. This is the property of water. Water is really weird. The only 2 things in the world that do have, well, I'll wait on that. First of all, we don't realize it because we spend a lot of time heating up water. Right? You're always boiling water and things like this, so we don't think anything about it. But if you were to try to boil other things, like for example, alcohol is a good example. It doesn't take much heat to boil alcohol. It doesn't take much heat to boil all sorts of things. Water requires a lot of heat to heat it up. It requires, a calorie is a big number, really. To raise 1 cubic centimeter of water at 1 degree Celsius takes a chunk of heat. That's a calorie. Lowercase c. So as a result, what happens is that aquatic systems are very, very buffered. So we all see this, like this morning we got up and it was, when I got up it was probably 70 degrees. It's pretty close to 90 now. Temperature went up. But if I took water temperature in a pond, it would have been about 50 or 60 degrees, and it wouldn't have changed that much over the day. The aquatic systems have very, very buffered changes. So as a result, it's kind of important to life in those systems. You don't see these massive, rapid changes in the system. The more water is in an area, the more buffered the change. That's why when humidity is high, temperature stays pretty much the same for long periods of time. Okay. On top of that, you add what are called the latent heats of vaporization or fusion. In other words, these are not only does it take a lot of heat to heat up water, and also as water cools down, it releases a lot of heat. Okay. Well, if I change water from gas or from water to a gas, it takes even more heat to change forms. So it sucks more heat out of the area. When water goes from a gas to water, it releases more heat. And the same thing if I change from, that's the heat of vaporization, the latent heat of fusion. If you take wet water and change it into ice, it's going to release a whole lot of heat. So again, all these things buffer. Okay? It takes or releases a lot of heat to change states. That's on top of the fact that it takes anyway. So these are some of these existing different changes. You're never going to ask these numbers. When water goes from a liquid to a vapor, you had to have over 2,200 calories to do that for every cubic centimeter. And if it goes from a liquid to a solid, you had to basically, it released a whole lot of heat too. So basically, these are kind of, again, add to different things. So basically, think about that. Water functions as a great heat bank. So water, basically, it's so on hot days, basically water is collecting heat. Water is changing from water into vapor. So, and that energy goes into the vapor, and it's up in the vapor, and ice is melting down. Ice is going from solid to liquid, and so that's banking up all that heat, taking it in, and then when the weather changes, basically it starts to release it. So again, our seasonal changes, this is what allows life on Earth. You go to any other planet that doesn't have water, and in a span of a day, the temperatures will change thousands of degrees. But not here, we would be shocked if we changed more than, if you changed 100 degrees in a day, it would be a shock. The last property then is the weirdness of the weird. And there's only one other thing that does this on the face of the earth, and that's liquid barium. Not a big thing around in the world. Okay. Barium and liquid. Okay. And that is that water, okay, density, most everything else, the density is greatest when they're in a solid. Water, okay, we already talked about here, as I chill off water, the viscosity increases, and that happens just fine and dandy until you get to 4 degrees Celsius. That is when water's at its most dense. Okay? And then what happens is, because of the shape of the molecule, we get under 3 degrees, 2 degrees, 1 degree, right before freezing, what happens is the molecules repel from each other. And as a result, they're less dense. So for those 4, of course, then finally you freeze a solid, it's less dense when it's solid, and from there on in, it's less dense than at 4 degrees C. So water being less dense as a solid is weird. Okay? Since water freezes at 0 degrees C, water is one of the only things that floats as a solid. And this has major impacts on life aquatic systems, needless to say. Okay? It's probably the single most important factor for life in aquatic systems outside the tropics. If lakes froze from the bottom, they could freeze solid. But because they freeze from the top down, the minute I put that film of ice on the top of the lake, in kicks the latent heat of fusion. So now that water's I've got the ice, a skim of ice forms rather quickly, but once this forms quickly, it serves as an insulator and it becomes harder and harder and harder. For lakes to freeze a foot, you have to have extremely cold conditions to suck out all that heat, the latent heat of fusion, come back out of there. So there's always, if it froze the other way around, you can just imagine all the fish would be flopping on the surface of the lake, and that wouldn't work too well here. Okay, so because of this, lakes do not freeze solid. There are no lakes that are frozen solid. Probably the only exceptions to that are very, very shallow systems, and the only possible one is Bonny Lake. That I can think of. Bonny Lake is in Antarctica. It's an extremely shallow system. It's considered to be the only lake that ever frozen solid. Okay, we did it.